There have been a number of major changes in the look of the SANS analysis package. The most obvious is the addition of a new interactive panel for loading, plotting, appending, setting up curve fits, and actually getting feedback from the curve fits. A familiar feature is the procedure list, which allows you to select different model functions and include them for use in the experiment. All of the features, instead of being under the macros menu, have now been consolidated under a SANS models menu. The first items allow you to call up the input panels or manipulate the model data. Additionally, the packages available are the same as were available before for summing models together, global fitting, calculating the invariant, or doing linearized fits. In addition, there's also a feedback button, which again will take you to a web page where you can enter a ticket for either a bug report or an additional feature you would like to see implemented. Now, when you are starting an analysis experiment, instead of loading data from a menu option, you can simply load the data using an obvious button. This works the same way as before, where you simply select the data file you would like to load and open it. This can handle the NIST-generated SANS data files as well as smeared or de-smeared USANS data. As usual, the data is plotted in a graph window and displayed. Rather than loading individual data files one by one, using a plot manager, which is very similar to the plot manager in the SANS reduction package, you can load files batch-wise. It does need to know where you would like to load these files from, so we can choose the folder of test data for the packages. And now if you wish to include a series of data files, simply shift-click to select them and load the files. It will sequentially load the files and ask you if you wish to append them to the current graph. In this case, we have a contrast matching series of spheres. In addition, when loading data, there's an additional step when loading USANS data, either through this option or from the Load 1D button. Loading a .cor file, where this indicates slit-smeared USANS data, opening the file will ask for you to input the high Q slope of your USANS data. Once you accept that slope, a calculation is done, which will take a couple seconds. And what this is doing is calculating a weighting matrix so that the slit smearing of USANS data can be done in a much more efficient way. This only needs to be done once when the data file is loaded. How model functions are included and plotted, either as standalone models or smeared models versus experimental data, is very similar but slightly different than it has been in previous versions. To load model functions brings up the procedure list as usual, and you can include model functions as are appropriate for your sample. In this case, for the apoferritin, we know that the core shell model is appropriate. Now, the data sets that are actually loaded into the experiment are listed here. We make sure to select the apoferritin and then select what function we would like to plot. If we plot a simple core shell sphere model without smearing, we get the normal dialog asking us for the number of data points, minimum and maximum Q values. A plot is generated as usual, and in this case there is not a separate table generated. The table with the coefficients _CSS for the core shell sphere model are shown in the table that is embedded in the panel. As usual, changing any of these values immediately changes the model. If, however, with the dataset apoferritin selected, you choose to plot a smeared model, it will tell you that it can't find the coefficient, so you need to plot the function. It plots the function, a graph is created, and immediately hidden. And then the coefficients for the smeared model are shown below. The coefficient list is the same as previously, but it has now been returned to the default values. We can append this smeared core shell sphere model to our apoferritin dataset by simply clicking Append. We can then, as before, change the coefficient values to be something reasonable to make an initial guess before doing data fitting. On the CurveFit Setup panel, the three pop-ups for the dataset, the function, and the coefficients now obey a specific hierarchy. Whatever dataset is chosen is linked to the function and coefficients below. For example, for the contrast match sphere 1 dataset, the smeared core shell sphere function has not been plotted relative to that experimental dataset and that specific resolution. However, the core shell sphere model, since it is simply calculated for a user-chosen Q range and number of data points, is not attached to this set, and the coefficients now are visible and can be changed. It's important to make sure when you're comparing a model to a particular dataset that that dataset is actually chosen in the pop-up. This dataset chosen will also be the dataset that is used for any of the data fitting. Okay, right now we'd like to actually fit the apoferritin dataset to a smeared core shell model. So we select the dataset, we select the smeared core shell sphere model, and it automatically finds the right coefficients. If we put in some appropriate values for the scattering length density of the core, and then hold these values fixed during fitting, we can see if it gives us a reasonable result. To hold a parameter fixed during fitting, simply enter a 1 in the hold column in the table. This table acts like any other table, and we can resize the columns to actually see the full parameter names. So in this case, we want to hold the core, the solvent, and the scale factor fixed, and let the scattering length density of the shell vary and adjust the contrast. We can also apply simple constraints to the parameters by applying a lower limit and upper limit. In this case, we can say maybe 10 for a lower limit and 100 for an upper limit of the core radius. We need to be sure to check the Use Constraints checkbox. In addition, you can use cursors to select the range to fit, use an epsilon wave. Occasionally this is necessary if convergence is slow or unstable. It's typically not needed. In addition, you can generate a report automatically with the data results of the data fitting. If the Save It box is checked, the report will automatically be saved. If you click on the Do 1D Fit button, it will do a 1D fit. If our initial guesses were fairly good, the fit will converge rather quickly. The report that is displayed shows the model that was fit, when it was done, the results for the parameters, their associated errors. If there's a 0, that means that the parameter was held during fitting, and also shows statistical information such as chi-squared, the reduced chi-squared, the actual Q-range fit, and if there were any errors generated during the fit. In addition, you see a graph showing the data and the fit through the data.